Okay. So, good evening, guys. Welcome to this live web streaming for the course Fundamentals of Electronic Materials and Devices. So, this is the first time we are trying this live streaming for this course. So, earlier, a couple of years ago, we had a chat session with a bunch of students through Skype, but this is the first time that we are broadcasting through Google. So, we are more or less halfway through the course. We have I have actually put up to week 5 of lectures online, and first 5 weeks are basically up to the end of PN junctions. So we are done with the electronic materials part of the course, and we have just started with the devices part. And I have published the lectures up to junctions. As far as the assignments go, we are finished up to assignment 3, which basically is the electronic materials part of the course. So at this point, we thought that it would be nice that we can have sort of an interaction session where you can basically post some questions. We had a Google form, a sign up sheet for that, and we can use that to basically answer some of the questions. So one interesting thing that I noted is that I also teach this course offline here in IIT Madras. I have been teaching for the last 5 years, and a lot of students have issues with drawing what are called these energy band diagrams. So these diagrams are very important to understand the physics behind the semiconductors. I use these diagrams extensively during the lectures, and a lot of students have issues trying to follow how to draw these and what information can be gained from that. So I thought I will use this live session in order to answer some of those questions. And also, one of the questions had asked about, one of the students had asked about tunnel diodes, which I normally don't cover during the course. So I thought I will also use this live session in order to answer those questions. I believe there is also a chat facility available for you to log in and post your questions. So you can also use that chat facility in order to post any questions while you're watching the course live. So let us take a look briefly at some of these energy band diagrams. So when we look at this particular course, we are mostly dealing with metals and semiconductors. So metals are, of course, very good conductors of electricity, while semiconductors are not so much. And we sort of explain this difference by using these energy band diagrams. So what I will do is I'll try and draw this here on the tablet and then share it with you live. So you can also see as I'm drawing. And I will also try and explain what I am doing while I'm trying to draw these diagrams. So just give me a couple of minutes while I try and figure this out, and then I will start drawing these diagrams. Barty, I need to share this screen. So how do I share this? Okay. So let us basically look at these energy band diagrams. First, I will start with metals. As I already told you, metals are essentially good conductors of electricity. And how we depict this is by drawing a diagram where we have a continuous band. We say that in the case of metals, both valence and conduction bands merge so that there is one continuous band. The top of this energy band is called the vacuum level. And we say that any energy levels above it are outside the metal and are not and are basically outside the metal. So the bottom of the valence band is usually fixed at 0, and then we have the top of the band where all the electrons are filled is called the Fermi level. So we say these levels are all full, these levels are empty. But the important fact to note is that between the full and the empty states, there is absolutely no energy gap. So the y-axis here represents energy. Because there is no gap, metals are said to be very good conductors. There are a lot of empty states available for metals in order to conduct. So this energy which I have marked EF is actually very important. It's called the Fermi energy, and the concept of Fermi energy will run throughout this course. We can contrast a metal with a semiconductor. So this is a metal, and then let me draw a semiconductor as well. So in the case of a semiconductor, we have two energy bands. One we call the valence band or VB. The other is the conduction band or CB. And we say that the valence band is full and the conduction band is empty. Most importantly, there is an energy gap between these two, which is called Eg, right? So for conduction to happen in the case of a semiconductor, an electron from the valence band has to be excited to the conduction band. This usually requires some thermal energy, and not a lot of these electrons get excited, which is why semiconductors are actually very poor conductors as compared to metals. So in the case of metals, I put the Fermi energy between the empty and the full states. So here we have a big gap between the full and the empty states. So by convention, for intrinsic semiconductors, we put the Fermi level somewhere in the middle. So EFI represents the Fermi level. It's not exactly in the middle. So if you look at the lecture notes, you'll see that depending upon the density of states, EFI will vary. But overall, the Fermi level is somewhere in between the valence and the conduction band, and it is usually at the middle of the band gap. So this basically describes the difference between metals and semiconductors. Usually semiconductors we don't use in the intrinsic state. We always want to dope them with some amount of dopants. These can be donors or acceptors. So when we look at case of a semiconductor with extrinsic semiconductor where we have dopants, now your energy band diagram will essentially change. So I'm drawing two semiconductors. For now, let us say they're both the same. They can be both silicon or they can be both germanium or gallium arsenide or so on. So this is my EV state. That's EC. One of them I'm going to dope with donors. That makes it my N-type semiconductor. The other I'm going to dope with acceptors. That makes it my P-type semiconductor. So how do you depict this on an energy band diagram? So EC and EV are all the same because I told you it was the same semiconductor. What changes is the position of the Fermi level. For an N-type semiconductor, the Fermi level is closer to the conduction band, so it's EFN, while for a P-type semiconductor, it's closer to the valence band, so it's EFP. So this difference in the Fermi level is because of the difference in concentration of electrons and holes. So that again leads to different properties. So one property that actually changes is something that is called a work function. So usually we have a vacuum level. I drew the vacuum level earlier in the case of a metal. And from the Fermi level to the vacuum level is called the work function. So I have here the work function for my N-type semiconductor. This will be the work function for my P-type semiconductor. And because of the way we dope, the work function for the P-type is always greater than the work function for the N-type. So that again tells you how the Fermi level plays an important role in determining the properties of the semiconductor. So these are basically energy band diagrams of metals and semiconductors separately. But the moment we talk about junctions, it is important for us to see what happens when we bring these together. So whenever we bring a metal and a semiconductor together, or two semiconductors together, we form junctions. And in this course, we have so far looked at metal semiconductor junctions, which can be Schottky or ohmic junctions. And we have also looked at semiconductor junctions, which are primarily PN junctions. So let us try and draw some of these again using these energy band diagrams to help us clarify some of. So let us look at a Schottky junction. So in my lecture notes, I basically use a Schottky junction between a metal and an N-type semiconductor. So I thought I will use this opportunity to basically draw a Schottky junction between a metal and a P-type semiconductor. So here I have, okay, so let me get my notes. So here is my metal. So this is my vacuum level, EFM, and this is my work function for the metal. So all of these energy states are full. So now I have a p-type semiconductor, and of course the way we draw a p-type is by drawing the Fermi level closer to the valence band. So this is my vacuum level, this is EC, this is EV, and here is my vacuum level, which is EFP. So this is again the work function of my p-type semiconductor. So now when I bring the metal and my p-type semiconductor together, I should form a junction. P is greater than phi m. That junction is basically called a Schottky junction. So a question is, how do we draw a Schottky junction and why is that important? So the rules are, whenever we draw a junction at equilibrium, the Fermi levels in the junction should essentially be aligned. So when we draw the Fermi levels aligned, so here is the Fermi level on the metal side. Here's the Fermi level on the semiconductor side. So EF in the metal side, and then EF on the semiconductor side. So a metal has a much higher charge density than in the case of a p-type semiconductor. So holes from the semiconductor move towards the metal and basically create a depletion region. So the dotted line, the vertical dotted line I'm drawing here, represents the depletion region. Because holes are lost on the p side, we say that, okay, yeah, so how do I see the comment? So just give me a minute, guys. Okay. Okay, that will screen share it. Okay. So it's already shared. So I can just toggle, or each time do I have to share, or no? If I go here, do I have to share again? No. Okay. Okay. Hmm. Okay. So, guys, I'm just reading some of the comments. So, let me actually finish explaining the formation of the equilibrium for the Schottky junction, and then I will try and address some of the comments. Okay. So, let me just get back to this diagram. So, again, this is the metal on the left, your p-type semiconductor on the right. So, we said that there is a depletion region that is formed because that you have holes from the semiconductor moving to the metal. So this creates a net negative charge on the semiconductor side and a net positive charge on the metal side, and we say that there is an electric field that goes from positive to negative. And the rule when we draw energy bands is that in the direction of the electric field, the bands should always bend up. So away from the depletion region, I still have my p-type semiconductor, so EC, EV, but basically I have a band that is bending up in the direction of the electric field. So these two will essentially join. So that way, I now can look at my Schottky junction in equilibrium. Okay, so that why do this? So that is in the case of a metal and a p-type. You can also draw a Schottky junction for a metal and an n-type, as I have done in the notes. So the reason, of course, why we have Schottky junctions is that because we have a depletion region, it will only transfer current in one particular direction. So a Schottky junction is a rectifier, so it will transfer current in one direction. So you have an exponentially increasing current in forward bias, while you have a really small current in reverse bias. So Schottky junctions are important because we can use these in order to form devices which will only conduct in one direction but not the other. So let me now go and look at some of the questions, and then I'll try and answer some of them. So one of the questions is about the trap states that are formed in between band gaps and how it will affect carrier concentration. So let me try and redraw the band gap for you. So whenever I draw energy diagrams for semiconductors, I just draw this. I say this is my valence band, this is my conduction band, and then this is my band gap. So this kind of diagram is something that we draw for an ideal semiconductor. And when we say ideal semiconductor, there are absolutely no defects within the material. So then there are no trap states. But in reality, that is not true. So most of us work with semiconductor materials where, depending upon how we process them, there are always some defects in the material. For example, in our lab, we work on zinc oxide, and the way we process it always leads to defects. So how do we normally depict defect states? So defect states are usually of two types. We call them one as a shallow defect, and the other is a deep defect. So another word for defect states are trap states. So you can also call them as shallow traps and deep traps. So just from the name, shallow states are states that are usually close to the band edges. So think of your dopants. So dopants usually form shallow states. Deep states are basically those that are further away from the band gap. So they are much more closer to the center of the gap. So presence of these defects will also affect conductivity. So if I have a shallow state, for example, in the case of n-type doping, we know that that usually leads to increase in conductivity. On the other hand, presence of deep states, especially trap states, can basically trap electrons in holes. So an electron, instead of going to the conduction band, can basically go and get trapped here, and then depending upon the lifetime of the electron there, it can affect the electrical concentration. So what we discuss in the course are essentially ideal semiconductors. I don't discuss how we make them, but most of the semiconductor industry makes use of ideal semiconductors, so people have been making them. But for most other semiconductors which people normally process by other means, it is the trap states also play a role in determining the carrier concentration, and that depends upon the actual semiconductor you have, and also the type of trap state and how you process them, that also matters. So hopefully that is clear. If you have any more questions related to this or anything else, please feel to please do ask them, and then we will try and go on with the rest of what I had planned. Okay, so we basically spend some time looking at the Schottky junction. So Schottky junction is of course one kind of a junction that is formed between metals and semiconductors. Schottky diodes are actually available on the market. The other kind of junction is called an ohmic junction. And again, I have explained ohmic junctions in my lecture. Ohmic junctions are what people actually need when you're trying to make electrical connections to your integrated circuits. So the circuit itself has all the rectification that it needs. And then finally, we need to make an electrical contact to the outside circuit. And so you need ohmic junctions. So people really need, when they actually make and design and fabricate these semiconductors, people actually look at what kind of metals they can use. And their choice of metals, again, depends upon whether they look for an ohmic junction or a Schottky junction. So I want to move on. We've seen one example of using energy band diagrams with the metal and the semiconductor, but I actually want to also look at how do you draw an energy band when you have two semiconductors. And these are of course your PN junctions. PN junctions are something that we have just started, and I have also posted the videos for lecture 5. So we want to spend some time to again brush up or revisit how we draw these energy band diagrams for PN junctions. Okay, so just give me a minute while I figure this out, and then we can start this. Okay. So when we want to discuss PN junctions, we actually look at both uh, kinds of junctions. So in one case, both the P and the N are essentially the same material. Those are called homo junctions. It's easier to draw them. And then I will then look at hetero junctions, not in so much detail. So let us say I have a P-type semiconductor and an N-type. So at the start of this live session, we basically drew the energy band diagrams for both. And we said that the only difference was how we position the Fermi level. For N-type, we put the Fermi level closer to the conduction band. For P-type, we put the Fermi level closer to the valence band. So this is again before the junction is formed. So when a junction forms, as I mentioned, for metals and semiconductors, we should have the Fermi levels line up. Another way of saying this is that electrons from the N side move to the P side, and then holes from the P side move to the N side. So this creates a net positive charge on the n-type side and a negative charge on the p-type side. There is an electric field that goes from positive to negative, and we say that bands will bend up in the direction of the electric field. So again, we can draw these. So this is my Fermi level. They are now aligned. So this is my P side. So I'm going to mark my EV and EC. This is my N side. So I'm going to mark my EC and EV. So because of the movement of electrons and holes, we basically have a depletion region that is created between the P and the N. We will not go into much of the details. You can look at the lecture notes for that. But there is a depletion region, and we say that bands bend up in the direction of the field. So remember, the field is going from positive to negative. So we say bands bend up, and same way, you also have a band bending up. So at equilibrium, we have an energy barrier. So this is your N side of the semiconductor. This is your P side. You have a lot of electrons here. But for these electrons to move, there is an energy barrier, which is nothing but your built-in potential. So EV naught. So for the electrons to go here, it has to overcome this energy barrier and then go on to the P side. Similarly, there are a lot of holes on the P side. They also have an energy barrier, which is the same. So let me just redraw this more clearly. So they also have an energy barrier to go across, which is why you don't have any current flowing in the case of a PN junction. So you can compare this energy diagram with what we drew for a Schottky junction, and then there are some similarities with the way we draw this. Okay, so let me then continue with this, and then I want to draw how the IV characteristics will look, and then we will see whether we have any more new questions and then how to address them. So when we want to basically flow current through a PN junction, we need to make an electrical contact. So we connect the P to the positive and N to the negative. This is called forward bias. So the same way how we had forward bias for a Schottky junction. So there is a built-in potential on the PN junction. So that is usually given like this. And there is an external potential. And the most important thing to note is that V external is in the opposite direction to V naught, which means you're reducing the overall barrier. And again, how do you depict this? Is that you draw your EFP, but now because I'm connected to an external circuit, you no longer have the Fermi levels line up. You have some energy gap between them, and that energy gap is given by the external potential. So higher the potential you apply, then more is the split between the P and the N. So I can again draw the rest of the gap. So this is EV, this is EC, this is EC, this is EV, and then I can draw the rest of make the band bending. So now your barrier height is actually lowered. It was earlier EV naught, now it is EV naught minus V external, which means I have electrons. They still have to make a jump, but the jump they have to make is less than what it would have been earlier. So in the case of forward bias, we find that the current increases exponentially with the voltage, which is again why we say that a PN junction is a rectifier, just like a Schottky junction, because the forward bias current increases exponentially to the applied voltage. In reverse bias, there is a very small current, which is called the reverse saturation current. We also have things like junction breakdown that happen, but again, those are things that I go through in detail in the lecture. So here what I want to do is to show you how by drawing these energy band diagrams, we can try and explain some of the characteristics of these junctions. So let me now go and look at some of the questions and then see if I can answer them. So again, so one of the other questions that has been asked is to basically look at the work functions of metals and what is a good electrical contact for amorphous semiconductors like silicon, or for semiconductors like amorphous silicon and zinc oxide. So let me try and actually answer this question in two parts, and then we will talk a bit about how we make these measurements. The kind of metals which are used for good contacts, that's something that I can't say off the top of my head, but I can give you some ideas based upon what we do in our lab. So what is essentially work function? So we say that work function is the energy that is required in order to remove an electron from a solid. So it helps to sort of go back to look at metals. And in the case of a metal, we have a Fermi energy. We have a vacuum level. And the energy difference between the Fermi energy and the vacuum level is actually the work function. The question is, how do we determine this? So there was this very famous experiment, or actually a very famous explanation, which was given by Albert Einstein. I believe the year is 1905. He actually won the Nobel Prize for this work, and which is nothing but the photoelectric effect. So the photoelectric effect states that if I shine light of some energy h mu, and h mu is greater than the work function, I'm going to remove electrons from my metal, and the energy of the electrons is nothing but h mu minus phi m. So h mu is your energy of the light. Another way of writing this is hc by lambda. So you write the energy, or this is the kinetic energy. So let me make it explicit as the kinetic energy is nothing but the energy of the light minus the work function of the metal. So if we can measure the kinetic energy of the electrons, and usually people do this by applying a reverse potential so that your current goes to zero, and they calculate what is the minimum potential you need to apply to stop the current, and that becomes the kinetic energy. So this can be measured. There are apparatus to do it. The light is usually what you shine, so you know the energy and the wavelength of the light. So this is known. From these two, the work function of the metal is calculated. And this idea can also be extended to semiconductors, can also use the photoelectric effect to measure the work function. There are other techniques as well. So Kelvin probe is another technique which is used to measure the work function. But again, Kelvin probe is something that I don't want to go here. But conceptually, the photoelectric effect is a way of measuring the work functions in the case of metals. So the second part of the question is what kind of materials that we need to use in the case of making contacts or junctions for amorphous silicon and zinc oxide. So again, the question is what type of contact do we need to make? So whether you're looking for a Schottky junction or an ohmic junction. So for amorphous silicon, I don't know. I haven't really worked with amorphous silicon, but in our lab we do work with zinc oxide. So for zinc oxide, we do know that when we make junctions with silver, it usually turns out to be a Schottky junction. Uh, Gold is also the same. In fact, if you want to make junctions with gold, palladium, and zinc oxide, they essentially turn out to be Schottky junctions. So the follow-up question, of course, is what do we do if we want to make a ohmic contact? So we haven't still tried that out yet. I believe copper will make an ohmic contact, but that's something that we are actually working on right now. And maybe once we figure it out, you can always contact me offline. You can also basically look at literature. So people also use tungsten as contacts, but for zinc oxide, I don't remember whether tungsten forms a Schottky or ohmic, but there are usually literatures that are available in order to help explain that. So one of the other questions that was actually asked offline is how do tunnel junctions work? So I thought that having looked at PN junctions, we'll sort of go from PN junctions and look at tunnel junctions. So tunnel junctions are interesting in that I don't talk about it in the course, but it is actually very easy to understand tunnel junctions once you use these energy band diagrams. Okay, so let's basically get a new page here. So a tunnel junction or a tunnel diode actually has another name. It's also called an Isaki diode, basically from the name of the person who actually fabricated it. It has a very interesting IV characteristics. So I versus V. Most junctions act as rectifiers, which means they pass current in one way and not the other. Tunnel diodes, in the reverse bias, they actually have a ohmic kind of behavior. In the forward bias, they have a region where the current increases with voltage, but more interestingly, they have another region where the current actually decreases and then it starts to increase again. So this region where you have your current increasing and decreasing is basically due to a phenomenon called tunneling. And when your current decreases with when your current decreases with voltage, we call this region a negative resistance region. So they have a very different IV behavior as compared to a regular PN junction. So one way to understand it is, of course, look at the energy band diagram. So Isaki diode or a tunnel diode. So let me take a new page and then I will draw the energy band diagram. So usually we start with two diodes that are actually very heavily doped. So in this example, I'm going to use Degenerate Semiconductor. Again, we have looked at Degenerate Semiconductor in the lecture notes. For those people who need some bit of a revision, a degenerate semiconductor is one where the Fermi level actually lies within either the valence band or the conduction band. So I have a P plus. We usually use plus to denote heavily doped or degenerate. I have a P plus and an N plus. So here my Fermi level is in the valence band. So if you remember from earlier, we were always drawing the Fermi level between EC and EV. And now I'm actually drawing the Fermi level below EV in the valence band. And here I have the Fermi level in the conduction band. So EFN. So these are essentially heavily doped semiconductors. So right now both of them are separate. We can then put them together. And when we put them together, once again we say that your Fermi levels must line up. So you have EFP and EFN. So you have EC, EV. Okay. So this is before the junction is formed, and the diagram on the right is basically when you have equilibrium. So because a tunnel diode is formed by heavily doped P and N, the depletion region is usually very small. So depletion region is of the order of nanometers. So you have a very small depletion region, and that is the one that is basically responsible for creating this tunneling effect. So here you have excess holes. So all of these are electron states. So you have a lot of holes here. Here you have a lot of electrons. So when you reverse bias, you basically have ease of flow of current, which is why you have a linearly increasing current in reverse bias. In forward bias, depending upon the applied voltage, you can basically have different effects. So I can draw some of these. So let me get a new page. So let us say I have a forward bias now. So this is my EFP. This is EFN. So once again, they are not aligned because I've applied a forward bias. So let me redraw this. So EV has to be above this. EC is here. So EC is here, and then EV is below. So I can join my ECs, I can join my EV. So now you have a forward bias, but you still have a possibility for electrons to tunnel from the N side. So this is my N plus side, this is my P plus side. You still have the possibility for electrons to tunnel from the N to the P side. So if I were to show this on the IV behavior, so this is the reverse bias side that anyway we have seen that it's only linearly increasing. So in the forward bias side, you have a situation where your current is increasing because the tunneling is still possible. Then I keep on increasing my applied voltage. EFN will start to shift up with applied voltage. There will be a particular point when your tunneling current is maximum, but as you keep on increasing the voltage up, as EFN keeps on going up, the tunneling actually starts to decrease. So you can end up with a situation like this. So let me see if I can just erase this and then redraw. Okay. So now I have increased my EFN. That is my EC. So let me just draw EV proportionally. So now I have a situation where tunneling is no longer possible because EC is above the valence band edge. So then your tunneling drops and then it reaches a minimum. But further conduction is still possible because your barrier height is also going on decreasing. Remember, this is V naught minus V external. So tunneling is no longer possible. So this region is basically where you have tunneling. But as the voltage increases, your current starts to increase again because now you have the regular injection of minority carriers, which is how PN junctions work. So this is your regular PN junction behavior. And then this is the tunneling behavior. So again, a tunnel diode or an Isaki diode basically has a different IV characteristics, and again that is because you start with heavily doped P and N type junctions, P and N type materials, and that basically causes a very narrow depletion region, which allows tunneling for some voltage region until the Fermi levels are so far apart that tunneling cannot happen again, and then your regular PN junction behavior is maintained. Okay. So there were also some questions related to semiconductor modeling, which was asked again in the Google forum. So semiconductor modeling is something that's much more involved. Usually electrical engineering departments have courses that are related to semiconductor modeling. So this course is more about the fundamental physics of semiconductor devices. So semiconductor modeling again is something that is beyond the scope of this course. So that is something that we will actually not be discussing here in detail. So if you look at the rest of the course, we have done up till week 5, which is basically till the end of PN junctions. So around next week, we will be releasing the videos which are related to transistors. Transistors are of course very important because your integrated circuits all work on transistors, and transistors act as a switch, which means by switching on and off using a gate, you can basically control the current flow in a channel. So again, those are things that you will understand using these energy band diagrams. So this session is something that I wanted to use in order to make you guys familiar with the energy band diagrams, so that if you have any questions related to that, we can answer. So once we are done with transistors, we'll be doing optoelectronic material devices, mostly solar cells, LEDs, lasers, and so on. And with that, we will be concluding the course. So we will keep posting all of the lectures online, and any additional reading material that which will be useful for you for this course, something we will post online. You can always use the forum in order to ask questions. You can also send us questions by email, and then we will try and answer them, and you know hopefully clear your doubts. So this is something that we tried for the first time here, the live streaming. So please do give us your suggestions, and then based on this, we can have more of these sessions, maybe especially closer to when the final exam comes. So with this, I don't see any further questions. So I'll basically end the live session now. And then any other questions you have, you guys can basically do this offline. Okay, thank you.